we want this panel to be with you guys contribute, ask questions all you want. If you guys don't have any questions, now chime in and ask questions. But we really want this to be more of a discussion type panel. All right. So Ignacio or Giorgio, please start. Introduce yourself.
So I'm Giorgio Regni, I'm the CTO of Seagate. We are a storage startup. We do software-defined storage at petabyte scale. So you take a bunch of servers, map them into one large pool of storage, like you do, John. What we do special is we have our own scripted file system on top, because we have both an object store and a database. So we give you access via POSIX. I know that Jim doesn't like it, but we give you POSIX access, object, all in the same platform. So we can mix erosion code and application. That's what we do.
My name is John Dickinson. I'm the Director of Technology at SwiftStack, where we've been working closely with Seagate on some of the Kinetic stuff, specifically with integrating into OpenStack Swift. I'm also the project technical lead for OpenStack Swift and one of the original authors there, and been working with that for the past 5 years. So inside of the kind of Seagate hard drive interworld, the purpose of Swift is to abstract away storage volume. So when there's lots of new technology as far as what's happening in actual hard drives, it becomes really exciting to figure out how to really drive efficiency and scale and things like that. Anyway, so that's and then I guess to complete the introduction, at SwiftStack what we do is a storage company that solves problems by providing management and monitoring software for OpenStack Swift clusters.
Hi guys, my name is Ignacio. I work at Seagate. I've been part of the Kinetic project for the past year and a quarter, year and a half, give or take. I'm also a PhD student at UC Santa Cruz on the Storage System Research Center there. My involvement with the Kinetic project started with the Python library, which the Swift are using. Then it moved on to actually doing the integration of HDFS with Kinetic using the Java library that Xiaoming developed. And right now, I keep working along with the libraries. We're also working with Jim on the new features that are coming into the protocol itself. Then obviously, once the features are there, I'm maintaining the library, so I'm working on the library. And I'm handling some of the clients, so I kind of know like what who's actively playing with the drives, because they tend to send me emails for Skype yelling, what's going on here? So, just get on there and they get fixed. And that's pretty much it with me.
Okay. So, what do you guys find? Well, what do you think is the most significant value Kinetic provides to the specific architecture that you've been working on? So you for HDFS.
Well, I guess I start. For the different systems I've been working on, I guess the main value is actually being able to truly disaggregate the storage portion from the compute. You have direct access from absolutely anything, either a client or a management layer, health monitoring, directly to the storage device, which is just the drive itself. That allows you to actually scale on a level that is like unprecedented and with little overhead. You could actually have, say, 1 exabyte. I mean, 1 exabyte would be like a little bit too much, but say that you have 1 exabyte and you're driving the exabyte from your laptop. You could actually do that with Kinetic Drive. Absolutely no service, just your laptop and exabyte. So you have some deep cold storage solution with absolutely no service whatsoever, and that can actually work. So I mean, obviously, all the way to the other point, once if you have heavy compute things, you can have a lot of CPU over there crunching data, moving back and forth between different drives and all that stuff, which is something more like what HDFS is doing. But the possibility of actually having something with absolutely zero CPUs on top of the drive themselves, it's totally possible with something like Kinetic. And like Jim was mentioning, like moving forward, the fact that you're not tied up with the processing, you're not tied with the file system on the OS, you just have an API that's talking to the drive, would allow you to actually access drives directly from your phone, access drives directly from the browser. I also have my own JavaScript library that accesses the drives, so you can actually show directly on your browser data, monitoring data from the drives, or even like actual key values that are coming out of the drives. So that's pretty awesome. And that's something like the community coding kind of thing. It's not something from Seagate. And I guess that's also something very cool from coming from Seagate on the main platform.
Everything you said. But actually, Ignacio said it well, Jim said it well. Those kind of like per drive storage benefits are really nice, and I mean ultimately that's the starting point. I actually don't think that accessing a drive from your phone is all that interesting or actually a good idea. Because the point is that we know that the hardware, regardless of who makes it, is going to fail. And so I think you need something there that abstracts away the actual data away from the media that's stored on. So you need something that's going to be able to use the word again tonight, the disaggregation of the data and the media. So yeah, driving an exabyte from your laptop is really awesome, but you've got to figure out which one of those hard drives you're actually storing stuff on. So being able to scale out to those levels is really awesome. And when I first started, when the OpenStack project just was launched 4 years ago, I started at the different meetups and conferences and stuff like this I go to. I started getting approached by guys like Seagate, HTC, Toshiba, and those kind of stuff. And they'd ask me the question, so if you could have anything you wanted in a drive, what would it be? And I was like, I have no idea, make it $50. You know what I mean? That would be great. And the thing is, I didn't even know enough about what was happening in the drives to even know what questions to ask, much less what the answers were. So what I think is really awesome is that you've got a complete change in how applications have been developed and how people are actually consuming data over the last 10, but especially 5 years, especially with the proliferation of mobile and data portability and all this kind of stuff. And I think Jim had the graphs of, about just how giant the data storage needs are getting. So the reality is that the applications are changing, they're driving the use cases, the storage media needs to change, but the thing is the app devs have no clue how the hardware works and treat it as this kind of dumb thing. And the hard drive guys have generally historically made something that's so generic that you don't really know actually what's going on there. And the only time those two things come together has been in the data center, and nobody actually ever goes into the data center, which is really bad. So that's kind of in general why I'm so excited about stuff like OCP and how an OpenStack and those things being able to allow the application to know something about how to share information with the storage media, so that when you say, I've got a picture, I need to store a picture, and you can kind of actually logically follow that this is a thing that I need to actually store. And for example, you'd say, I've got this cat photo, and I'm going to put it in Swift, and Swift is going to be able to talk to Kinetic drives. Do that today. So when you do that, the entire chain all the way through it, you can know that what was actually stored on the physical media is logically tied together. Whether that's your video, your user-generated data, all your backups, all of that kind of stuff. And what that means is you can remove all of those layers of abstraction that basically just add all the complexity and cost to things. So that's, to me, what's super exciting about it. Being able to not only just remove the things that add costs, both financially and time-wise, latency-wise, but being able to say that now the drive itself can participate in the logical reconstruction of the entirety of the data. And the application can actually hint to the storage media, this is the kind of data, and this is how we need to store it. So that's the kind of stuff that I really think is awesome about the whole Kinetic protocol and being able to actually implement that.
So one thing we like with the Kinetic drive is that server drives are not a bunch of sectors anymore, that are much more complex than that. And this is what we see on Linux, you see a block device. So I like the fact that somebody like Seagate knows the drive because they do, and are going to do the software that intelligently manage how you do a drive. So there must be a better way to write. Jim said that it's mostly sequential bytes of a drive. That's the best way to do that. They take care of it. I don't have to think about it. So I like the fact that the API is clean, it's very simple, and they can change the hardware behind. They can make it, full SSD, or better, and keep the same API. So that's something that I think is a good loosely coupled interface. The other benefit, I think you talked about that as well, is the fact that you decouple the compute and metadata from the actual data storage. And the data needs to scale. The metadata is small, data is huge. So that's a big benefit. And the biggest limitation we see today on regular servers is the bandwidth. So if you have a box like a 4U machine with 72 drives and 2 10 ports, the limitation is the bandwidth of that machine. You can daisy chain another 4U, another 72 drives, guess what? The PCI Express bus is not fast enough. So the fact that we can go directly on the network to the drives from the app means that we can save on interconnect, and my Xeon can do erosion code as opposed to being pushing buffers around and taking CPUs from them. So I think that's interesting.
Yeah, I think adding on both what you guys mentioned and what I mentioned before is like the ability for the API, the Kinetic API, to be the API that talks about the key values, and no matter what's actually behind the API, if you're talking to spinning Rust, if you're talking to SSD, and mentioning that we also have a daemon that is implementation of memcached that talks Kinetic, so you actually now have also direct memory access to through the Kinetic API. You can actually touch all your different levels of storage through the same protocol. I'm pretty sure someone, if they grab a couple tapes, they can come up with an implementation that goes from Kinetic to tape, so you can actually have one API that talks to all these different levels of hardware. We have different latencies and performance that would allow you to actually, based on your SLAs on your system, decide where to put them. Like metadata, let's go to this API because we know that's actually RAM, and this piece of data is actually inside for cold storage. Let's send it to this other API, which is like some hard drive, and these logs, let's just send them over to first layer of logs, let's send them over to some SSDs because we're going to be needing them quickly if the power goes down to rebuilding and things like that. I don't know. But I mean, the ability to have the same API through all these different hardware is actually pretty fucking cool.
Yeah. Yeah, question. So, John and Giorgio, I'm curious in your thoughts on a Kinetic SSD and how useful that would be and how you might use it.
So the Kinetic are very slow at random reading. So if you have a lot of objects, they're very slow, fucking slow maybe, at a random read. And we do have a lot of metadata. We need to manage folders, we need to manage buckets, we need to index a lot of stuff. So Kinetic SSD makes sense for to manage the metadata.
I think it makes the whole Kinetic ecosystem a whole lot more interesting. And one of the reasons is that if you look at the different cells in sort of a particular flash device, and being able to much more gracefully handle failures and partial degradation, which is a lot harder in spinning drives. I mean, maybe that's possible. Let's keep talking about that. But looking at, say, I think just this one flash cell chip died, but all the rest of them are fine over the same bus. So that's just kind of like on the hardware recovery side of it. I think it's really interesting because I no longer have to deal with this one thing that's I can shrink my failure domain, which is really nice. And number two, I think it's really interesting because, of course, more power, more numbers, more better. And specifically, one thing I would love to explore, not to go into too much technical detail, but we have a couple of pieces inside of Swift where we do some metadata sort of things, where we, for example, keep listings of subsets of the overall key space. And those things can be rather IOPS hungry. So being able to actually, instead of on top of a file system, implement a little library-based database where we can keep track of that in a structured sense, wouldn't it be kind of cool if we can just directly store that inside of Kinetic keys and values? Because really that's all we're trying to do is just an ordered representation of keys and values. So being able to do that on Flash. Now if I could even get even crazier, what if you had different kinds of media where you had different memory access patterns, where you could do like the direct memory access sort of things, remove some extra stuff. Is there something between RAM and Flash today that you could actually do? I don't know. I don't know if Kinetic is appropriate for those things, but it's at least a really interesting idea. So the answer is yes.
Good. We like the answer. We like crazy.
Really question SSDs actually.
I'm sorry?
Really question SSDs. So SSDs for million IOPS when you device something about gigabyte. It's not a real issue when you're going over the network. Actually, saturate the flash device.
Yeah, but that's not any different than what it is today, because generally your application a lot of times is actually over the network, away from your flash storage anyway, and so you're still going to be limited by that. I mean, that's not always the case. I mean, the whole data. Well, there's two different realms of thinking there. I think you've got the whole data compute locality sort of thing, but granted, my perspective is giant, massive object storage systems, which are really just kind of treated as a pool of storage on the other side of the network. Think like S3 in your own data center sort of thing. Rather than I'm going to actually be doing, say, high frequency trading on a map, the loop stuff that's right there next to the storage. One thing I think is interesting is that we've got a customer that we've been talking with for quite a while, and that's the whole disaggregation of the storage on the other side of the network away from the application servers is actually exactly what they're trying to do at very large scale. Instead of tightly coupling them, and they're also moving to like flash everywhere in their data centers, which is another interesting development. But the point is, they want to separate those things basically because scale demands specialization. You can't just say, I'm going to have a million IOPS and a CPU right next to everything. There's some things that are really good at that, but when you start dealing with petabytes and beyond and thousands of CPUs and beyond, you kind of need to be very flexible and separate those out. And so, yeah, it's really great to say I have a million IOPS, but you've still got to, let's get crazy and say you've got a 40 gig network between the two and 100 gig network next year. It's still, yeah, the network is absolutely a problem.
So there's just one observation on that too. One could envision that the way that there's value being made in the system object storage protocol across tiers, but the exact implementation of a enabled SSD network.
For the question on the SSD side, object store typically is like write once or read many. So would SSD make sense from the price point of view? I mean, you can get the better performance, but if you're writing just once and basically maybe is it cost competitive to hardware?
So I guess in our case, we will not use SSD for data storage because it's a waste in terms of cost. We use the SSD just for indexing, being able to find the data quickly, being able to open a folder very quickly. This is what we use for SSD. And then to go back to the question of network, I think the RDMA stuff is very interesting because if you have 100 Kinetic SSDs, access from one machine on the TCP network, you're going to have a lot of overhead just because of TCP. So going to RDMA, which is in the plan, from what I understood, is a very good idea.
Yeah, but you're both
So I guess one of the ways an object storage is thought of is for unstructured data only. So I think one way I interpret that question is you have explained indexing and whatnot, makes absolute sense, but are there any apps outside this thing that can actually take object storage out of this, cheap, whatever, cold storage kind of thing? Are there any apps that you can think about?
I think of what you're doing right now. Every single backup and storage solution out there, and like picture the old Megaupload. All those little services nowadays that do upload files for you and download files, you could go straight to a backend with Kinetic drives. No service, almost no service in the middle. Just some metadata servers that are mainly handling the metadata with the SSDs, but you could actually handle that infrastructure that goes directly from your computer and gets the data from the storage device, obviously after going to some metadata server and getting the authorization. But yeah, that's one solution for it. And a lot of backup solutions can also do it if you actually add if you're actually feeding some the modifications with memcached that are actually doing the duplication on the key value level. You can actually hit those first that are then backed by real Kinetic drives and just forward those requests that are actually not deloopable and create the new chunks. Then you have a backup that's actually deloopable on a 1 megabyte level. If you want to do it at 1 megabyte level, you can actually do variable sizes too, but it doesn't matter. The point is, all these solutions, you can actually implement it and have some minor pieces of server components that you do need to have, and then the client just go get the authorizations or do whatever they want to need. Sometimes hit some middleware, sometimes don't hit some middleware, but they can actually access from the different computers directly to the drives. And everything that is millions of computers accessing the cloud, it's direct. It's something that directly benefits from the Kinetic drive. So you can actually now have a lot more parallelization on the amount of clients that you have going to the drives that you have in the back, instead of actually tunneling through always through the frontline server in your data center. So, I mean, that's just like top of the head some solutions that you're gonna have to come up with.
Right. Yeah. But another thing I was thinking about was if you have a lot of flash or something, as you said, something between RAM and flash. Probably I don't even have to use key value store. Right? Probably I can come up with like a hardware key value store.
But everything's key value.
Yeah, everything's key value.
I mean,
Even a file system.
I mean, you probably don't even have to go to object store and keep your metadata there. You can have it right at the server.
So it sounds like what you're talking about is not necessarily what an object store is or what's appropriate there, but really just kind of like different tiers of storage. You've got things that are appropriate for hot storage, things that are appropriate for cold storage, and I think the kind of interesting thing, especially as Ali is mentioning, is let's do it in flash, let's do it in spinning drives, let's do it in other stuff, is how can you optimize the storage itself specifically for the data that's stored on it. And a little plug, I guess, it's one of the things we just released in Swift is the concept of storage policies. And in fact, one of the reasons we did this was actually somewhere halfway between indirectly and directly the result of some of the Kinetic work. Because we want to be able to say, here's a massive Swift cluster, you've got these spinning drives over here, let's deploy some other stuff on SSDs here, on traditional hardware, and then let's put another storage policy over here that's Kinetic. And then we can kind of gracefully migrate over time, if that's what the deployer needs to do, or more specifically, I guess it's this particular subset of the overall hardware footprint meets these certain requirements with TCO or SLAs or something like that. So you're absolutely right that different data has different requirements, and being able to have a disaggregated protocol like Kinetic makes it actually possible without having to do massive pain on the storage application side, and that's a good thing.
Why not hybrid drive where you can provide the protocol saying, okay, keep this data on SSD or flash,
right,
and then write the big user data.
Yeah, I mean that's a system level kind of thing. Like this set of IP addresses belong to devices that have these particular metrics on performance and performance, either bandwidth or latency or whatever, and then these other set of IPs have these other characteristics. So based on your data, obviously your metadata, you're not going to send it to this low, high latency device. You want to send it to the one with the low latency. So you're going to send those, right? I mean, you're going to your system that you're building on top of the Kinetic architecture is going to make those choices based because he knows what he's actually trying to store.
And I think the point is that with Kinetic I don't have to think about that. As an application developer, I've never had to think about hard drives in the past. They've just been entirely unreliable and slow. Now, I still don't have to think about them, but the drive manufacturers can be smarter about it and make faster stuff. So if it's a hybrid drive, I don't care. If it's a flash device, I don't care. What I care about is I can, at a systemic level, treat the drives, take the data and make sure that it is durably stored across a lot of drives and make sure that we can effectively provide high access, high durability, whatever you need there. And I can classify certain things, just as Ignacio said, saying this is fast, this is slow. But the point is I don't have to think about it. And I can let the people who do need to think about it still think about it, but I don't have to. And they can change it out from underneath me and I still don't have to think about it. And eventually, getting into other stuff, I want every drive manufacturer to have the same sort of protocol there so I don't have to even go to a single vendor. I need to have multiple vendors that can each offer their own whatever it is.
Actually, I hear that on the key, object key, so storage policy can be specified. This object is going to go to fast storage or slow storage.
Yeah. Yes. Exactly. I didn't hear the question. Sorry.
Oh, sorry. I heard or read in some presentation that on the key object itself, you can specify the storage policy.
Are you talking about inside of Kinetic or like?
That's one.
I'm not sure where I read.
Okay. So I think the actually interesting thing is, that, at least from my perspective, the Kinetic is here is some keys and small values, and then when you have other systems like Scality and Swift on top of that, they can piece those together and put together your 20 gigabyte video cats, and then the system itself is what's abstracting out how are those actually persisted across, and then we can effectively do that with the Kinetic API. What we're having to do today is talk to a file system with positives. So it's...
And to add to that, I think there's a lot of value into not knowing what's below. So you need to make sure that you know the characteristics so that you can design a good system. But if there's an hybrid drive, I will let Seagate manage the log. It's a log structured system, send the log to the flash, the other part of the drive. I don't want to care. I don't want to deal with it.
Just like you don't want to have to deal with blocks and cylinders now. You don't want to deal ultimately with, how is that done? You want to be able to hint to it to say, here are 50 keys or 50,000 keys. They are logically tied together. If one of them dies, tell me that all of this whole thing is corrupted. But beyond that, that's all the drive needs to know about, and they can deal with all of that. Which,
so one quick question about this Swift use case for Kinetic, right?
Yeah.
So Swift has proxy and storage node. With Kinetic, they are not going to get rid of storage nodes, right?
That is
Once
correct. Yeah.
What is the benefit of having an key value interface over the network if they cannot get rid of storage?
I think the value ultimately is, the immediate value today is that, just the same things we've been saying so far. But in Swift, you've got the proxy servers, you've got the storage nodes. We have no plans at the moment, regardless of what Seagate wants us to do, removing those storage nodes. Ultimately, yeah, we could probably do that. And in fact, some of the stuff we've talked around the office is you remove the actual separate hardware and just make a little local connection. Maybe that's something that it's actually an operational thing rather than the actual where's the code living. But the point is that for the short term, the reality is there's not a lot of people who are buying Kinetic drives today. And so what we need to do is have a migration path over time. And so we entirely expect to have hybrid Swift clusters. And to do that, we still have a lot of value inside of Swift, and inside of Swift, the object servers, the storage nodes provide a lot of value. The really kind of cool thing with Kinetic is it makes those much more lightweight, so that, yeah, we're still doing a little bit of, we might have an extra hop that we can make more efficient later over the network, but we can still do a lot of the Kinetic protocol stuff and have a lot more drives behind a single storage node, massive improvements, but also combine that with, we've got traditional drives that people are doing now. We can say, hey, just plug in your Kinetic drives to the same existing storage node that you have today, and now you've just increased your storage density without actually having to increase your actually CPUs that you're deploying. Becomes interesting and offers that kind of migration path over time from saying, in the world we live in today, to a Kinetic future sort of thing. So,
sorry, one other objection on that is, while in the current implementation when it's read, you don't, kind of eliminate that, the logical object server functionality.
right.
What we do is, and we've done this in our labs in Longmont, we're running large scale clusters of this, is we do physical clusters.
Yes.
So the physical hardware goes away, and we actually have not had to increase the processing in the processor to be able to do the full functionality. So while we do see a more optimal architecture going forward, even as a first step, right, moving into all that physical hardware out of that.
Yes.
So we have the logic hasn't necessarily changed significantly yet, but the total cost of ownership has changed massively.
Another item that's different about, even though those object servers are there, they're now virtualized. They're not captive to owning an exact 30 disk drives.
Yeah.
If these 30 disk drives become cold, and another 30 disk drives become cold, another 30 disk drives become cold, well, why don't you create another virtual server that's managing 90 disk drives instead? And we've broken the link. We've disaggregated the system so that the object nodes are no longer physically tied to a cable to a physical set of disks.
Yes.
Thank you.
Yeah, I think the deployment scenarios we're talking with Clay were like all proxies were able to contact all objects, and all objects were able to contact absolutely all Kinetic drives as well. Eventually, you can actually have a Swift deployment that's like that, where all the proxies can talk to all the other object servers, and all those object servers can talk to all the drives. So even if you actually take away one of those Paco servers in Swift parlance, if you take away one of those Paco guys, all the other remaining Pacos can still talk to everything else on the infrastructure. So it doesn't really matter. I mean, yeah, you're going to lose some overall bandwidth because you just lost one of the proxy guys, but that's going to be equivalent to 1 over whatever number of proxies you have.
And a lot of that management stuff, that operational deployment choices really just comes down to your deployment choices of Swift is not actually the Swift code, it comes to the management solution that you have on top of Swift and how do you deal with that and do that effectively and cheaply.
So, we have got a lot of application and awareness in the connected drives. So do you see any caveat there that applications are changing or evolving, for example, Hadoop? So these kind of things are, new kind of applications are coming up every day, or the existing things are changing. How are you going to keep up with that?
We can always, I think you can only change in response to the applications when you see the applications change.
Yeah, but then hardware upgrade is kind of, it's more, software upgrade is more cheaper than hardware upgrade.
It is, but the cool thing is now all we're doing is talking to software that we don't care what the hardware background is. I mean, yeah, you can. It's the same question as when are you going to move to SSDs away from spinning drives? And you know, if you're in this brave new world of everything's kinetic everywhere, then the hard drive cost actually, I mean, the hardware cost, switching cost, seems like it would actually be less because you don't have to actually worry about the changing of the protocols or the port configurations or anything like that. You can suddenly, if you're talking on the network, which everybody's doing today anyway, then you can change your hardware without having to. You don't even know where your hardware is anymore.
Maybe let me add to a question. So once the stack and network functionality gets integrated into the drive, which let's say an array of 200 terabyte was there, and now instead of that I've got drives which are 200 terabyte which talk network directly. Today if I have to get some functionality inside the drive, a lot of times it's not inside the array. I do software upgrade on it. Sometimes you do get hardware, like you put a, instead of 1 gig, put a 10 gig card there or get RDMA card. Once the functionality is integrated in the hardware, does that mean I need to change the drive now? Or would you have software patches for the kinetic drives?
Yes, you do have software patches for the drive, and you install it like there's a command inside the Kinetic protocol that's just like firmware update, and you just send in a value that's basically the firmware binary, and it updates itself and reboots and comes back up.
Okay.
And you do that from within the protocol. That's all.
So I agree that it's always the drive is software, so we need to update it. What I like on Kinetic is the drive doesn't do a lot. We talk to other vendors where they want the drive to be a cluster as well. So now if it's a cluster of drives working together, now the software piece is going to be even harder. It's going to be a million of code instead of being 100,000. I don't know what's the number. So the software is simple enough that it should not have to be updated every week.
Right. I mean, maybe the thing came to my mind because it said we could go from TCP to RDMA, for example.
Oh, right. Yeah.
So and just obviously there's at the scale that we ship drives and we deploy drives in these environments, there's no scenario where any sort of an upgrade is forced, right? If customer X sees value in moving to RDMA, then and that's something that they can upgrade, they can choose to do that. But there's nothing, the way we've designed the protocol, and the way Google Protocol Buffers works, there's no reason to believe that there's ever a, oh my God, we have to all upgrade, right? You can, if you see the value in the change firmware, you can take advantage of it if you choose to. If you don't, so be it, no problem.
So something that's collaborate in the house. Actually, we're going to talk about solve the one overhead graph I was showing earlier. How do you sort of do it called extra operations?
That's actually, that's fine. So, yeah, I guess if you don't want to take that one.
That is for you.
Actually, that's just pure upstream Swift. So the interesting thing is that was actually done here at EVault, and Tim from Seagate was running a lot of those tests from their side. The way Swift works today is that when you get down that storage node, you have a box that looks like one of those, and you have a bunch of hard drives plugged into it, and every hard drive is simply a local file system. And all of those operations there ended up being a lot of those file system metadata overhead sort of things. The fact that, yeah, we've got to figure out what directory was that in. Okay, now we've got to walk to that directory, we've got to figure out what's going on there, we've got to do the fsyncs, we've got to do the flushes, we've got to do the moves, we've got to do the writes. And it was those low-level operations that actually came from things like XFS. All we're doing is saying, oh, it's got right in a loop.
Yeah, I mean, I was thinking that the M time being updated, length of the inode being updated, but most of these things, you know, like traversing through inode should be indexed, right?
You would think that, wouldn't you?
Yeah, I mean,
But
I HFS, right? And like, they're very similar sort of thing where we use local file systems underneath. I'm pretty sure we don't have a call to ratio over there. Pretty sure, I'm just saying.
So, that is, some of that has to do with some of the kernel to user space, but no, it's not, because they were talking specifically on the drives.
Yeah, exactly.
So that, when it gets down to actually the drives, you know, I think there were, since it's, like you said, it was 18 months ago that they ran those things. Since then, I believe there's a few things we've reordered to do less syscalls. But ultimately, it comes down to those inefficiencies in I'm trying to figure out what's happening. What we do, let me back up just a little bit. What we do is we write on that file system, figure out where it is, find out what's going on, read some metadata that might be existing there. We write it into another location. We do an atomic move once it's been flushed. So, and so it's that combination of things we're doing to provide the durability and the guarantee that the data is securely written, and when you're streaming out 20 megabyte objects, it ends up doing a lot of those little things. And then when you see those flushes, well, that's when the data actually got there. That was good, but it's all that little overhead of the other stuff that really.
Using a lot more than just all that stuff, right? So
yeah, okay, you're right.
One writes this call and out goes like 12 other operations.
Yeah. Now, here's some cool stuff that's actually being worked on. We've got a patch out there for some zero copy stuff, which using some kernel sockets, it is very cool because you've got some cryptographic sockets where you can actually say, write into this, but don't tell me any of the data, just tell me what the checksum is when you get when you're done. Which means that we can do some zero copy writes down to the drive and still get cryptographic checksums on them without ever having to see user space, which is really kind of cool.
On top of that, Kinetic actually has support for zero copies on the Python library as well. So
that's good.
Yeah, read and write.
So it's that kind of stuff that we're working on today in the community, and also looking for. That's the reason some of the other advantages of stuff like Kinetic.
Will the zero copy read your region of the network or over a socket?
Mine?
Yeah,
basically, it's two file descriptors. So essentially, you can either read directly with zero copy from the drive into a file, or read from the drive into another socket that's going to another server. Which the use case was primarily for the object servers on the Swift layer. So actually, the object server is going to have two sockets. One of them is the data coming from the proxy. Because when you're talking to Swift, you're tunneling the data from the proxy, and then from the proxy it goes to the object server. So essentially, the proxy is going to do a zero copy along with the crypto thingy to get the checksum. That's going to be tunneling directly to a socket on the object, which essentially is a socket on the same computer anyway because you're doing a Paco. So that's also going to do a zero copy from that guy to using the Kinetic protocol zero copy. That's going to send it to the socket onto the drive. So in those cases, all those guys are all socket to socket, socket to socket.
But in general, it means that we don't have to copy we don't have to take a buffer 64K or whatever it is, copy it from kernel space to user space, move it to the other socket, copy it back to kernel space, and then send it out the socket. We can just say, hey kernel, just take it from this file descriptor, put it in that file descriptor, and that's all we have to see. Basically, that's the zero copy thing both on the sides. And doing that in the Kinetic protocol also means that it gets more efficient.
And given that it's Python, it also avoids a lot of concatenation of strings and those slow things Python has. It's very slow.
I can saturate a 10 gig pipe. You don't need faster than that.
So, does the combination of Swift and Kinetic, I don't know, maybe the question is to you. So, erasure coding versus replication?
Not my decision.
So
It doesn't affect us.
yeah, actually that's kind of the cool thing about it. So I can tell you what we're doing on that right now. Swift has been a replicated system for quite a while, since it began, which has always been kind of really good for the use cases that it's really good at. But as you guys know, it's not the use case that is good for every single kind of data. And the storage policy stuff that I talked about that we just released is actually the foundational pieces of adding in non-replicated storage so we can do erasure coding. And that's what we're actively working on right now. We've got some guys here at EVault that are helping us out with that, including Box and Intel and Swift Stack. And so what we're expecting is probably in the time frame by the end of the year, we'll have storage policies that, and an erasure code storage policy inside of Swift. The good thing is, so you can now store that way, you can store replicated storage the other way. And as Ali said, it doesn't really matter at the drive level, whether we're using actually Kinetic or not.
Actually,
Giorgio, do you want to touch on that as well?
I don't want to break it. So we have erasure coding since 2 years now. So, and what we like about Kinetic is the fact that it's not trying to do that for us. So our objects are this size. You can put an object as replication, put an object that was deployed, whatever parity you want, and it doesn't change anything for Kinetic. We just take big objects, split it into pieces, send it to Kinetic, whether it's replication or erasure code. Kinetic doesn't have to know.
But your policy of erasure coding, right? You could have 54 or you could have 26 of them. So that would affect the size of the key value. So I probably would be underutilizing.
Let me add that I actually have like 30-40 lines of Python that do the erasure coding based on a data stream coming directly into the a set of Kinetic drives, and actually do distributed writes and reads based on an erasure code.
So that's
I can make that public. Just a simple
Won't there be
erasure
internal
based on Kinetic.
fragmentation? There probably is internal fragmentation, right? You won't be able to use the
What internal fragmentation?
No, because you've still got the 1 value, the 1 megabyte values. Right?
When you're doing erasure coding, all your words are the same size. So essentially, what you end up having, if you have, like, say, a video, and you're going to do erasure coding not across multiple data streams, but within the same conceptual object. So your 500 megabyte video is going to be transformed into a 550 megabyte actual storage because you're doing a 10% overhead, whatever mathing you want to use for that one is, say you want to do like 10 plus 2, whatever read all one, okay? So you're going to grab you're going to be caching on memory 10 megabytes. You're going to be sending those 10 megabytes to 10 different drives, okay? Then you're going to do the read all calculation for getting the extra 2 pieces. And you're going to ship those 2 extra pieces to another 2 drives. And then if you only had 12 drives, then you're going to come again the next 10 megabytes and you're going to send to those 10 drives. But obviously if you have like 30 drives or 60 drives, that's going to be interleaved. So you're going to be grabbing 12 drives and then another 12 drives, another 12 drives, and you're going to come over, maybe you have 8 there and then 4 here and then 12. So it actually ends up scattered, kind of like what you see on the picture for RAID 6. But that, all the words are actually the same size. So if your system has 1 megabyte words, 1 megabyte chunks, then you're actually doing the calculations on a 1 megabyte level.
But you're assuming large transfers and large.
So the way to manage if you have a very small step for erasure code is you switch automatically to replication. So if it's below
to what?
Yeah, if it's 12 bytes, you're not going to do erasure coding.
So you go directly to replication in that case. Because it's too small, so apparently you go to replication.
Right. That could be one of the storage policy probably.
It's a system level.
Yeah, it just sets up the thing.
But
you got to stand up first for that to shoot.
So now the drive has moved up in the functionality, right?
Yeah.
Instead of does that mean that it has moved up in the food chain also, and does that mean that it reduces the importance and the complexity of the higher level services like stability and
I don't think so at all. On the one hand, the drive moves up in capability because it's doing a little more, but I think that's hard to say. I think it's actually doing things smarter. That doesn't necessarily mean it's taking over more of that, but it does mean that from the holistic system view, that the drive takes over more of the functionality that, for example, the CPU was doing. So as far as the whole solution, yeah, it's really good for drive manufacturers because they're getting more of the value chain overall, instead of, like Tim said, Intel. I happen to like Intel, but they don't, so that's okay.
So I'll tell you a little anecdote about that. So we, the very first time we sat down with Joe Arnold, who you guys probably know, John works with SwiftStack, and told the story. Clearly, I didn't do a very good job telling the story because his first reaction was, "What the F are you talking about? That's what we do." Right? And I was like, "No, let me try again. And at the end of the hour meeting, he goes, "Oh my God, I have a really small team of guys, and they spend a fair amount of their time mucking around in file systems right now. You mean they don't have to do that, and they can actually focus on the stuff that's differentiating us? I'll take it every day and twice on Sunday." Right? It's just shifting. It's taking away the dumb stuff that these guys have had to do and saying, "Let us make mistakes."
So, follow-up
Is that
question,
fair?
what if Kinetic doesn't stop their ads proxy or application junctions in the client level?
So I think that's exactly what Giorgio was talking about, is that it becomes it's not only, it becomes a much more complicated system. The point Jim was making about, we know it scales because it's just right there. It's the simplicity scales, the small, concise, autonomous pieces that collaborate rather than something that tries to have a systemic view of everything. That's the kind of thing that scales. And if you have drives that try to say, well, now if I plug this drive in, it's going to self-organize and it's going to know how things do, then I've got to essentially, in my level, you've got them almost fighting with one another, which means that nobody's winning. And I mean nobody, I mean the customer is not winning. So it becomes, from a business sense, to be honest, it becomes very difficult to work with people who are trying to compete out from underneath you. From a technology sense, it becomes very complex, and from a customer sense, it's just complicated and failure prone.
I think it's a very clean cut. So the drive takes care of, it's a key value database, that's the only thing it does. And it tells you if one of the value is broken. So that's all we ask. And then on top, we manage our responsibilities with durability, making sure that we replicate when we miss copies and make sure that we do the policies and interface with the application. I think it's a very clear cut, and that's why we like the API to really use it.
Mario has a hand up next.
Well, I was just wondering, on the topic of erasure codes, does an Ethernet connected drive help? Is it the same as a SAS connected drive behind a classic storage node or behind a controller, or does this new unit of measure help with erasure codes? Because for a lot of people, planning the physical layout, where you put the drives for an erasure code scheme, can be complicated.
For me, given that I actually did the low-level erasure coding on top of the drive, it helps a lot because when I'm doing recovery, I totally forget where on the drive the data is supposed to be. I just the drive tells me this key is failed. Awesome, I'm gonna keep the recovery for that key. That means I go read these other 7-8 drives. So you have again, the example was 10 plus 2. So I'm gonna go read these other 11 drives, and I'm gonna do some math on top of it. That's gonna give me this other guy. And then I'm just gonna either send it to the same drive if that was an isolated failure, or I'm gonna, if the drive has been crapping out too much, you know what, I'm just gonna kill the drive and start sending this recovered piece of data over to another drive and slowly start recovering everything else on the drive. But even if I put it on the same drive, where the drive actually stored that, the drive knows those sectors that corrupted the key are no longer valid. The internal software running inside the drive is going to figure out where else to put the same. But from my point of view, it's the same key value. So if anyone else is coming over, I don't need to go update where in the drive something is or move files around in different folders or anything like that. It's just same key value and the same IP address. Or you know what? Now this drive is remapped over there and go fetch it over there. Because the drive has been losing too many bits too often, so it's probably going to die.
I think.
Can you ask again?
Oh, that's real simple. Hey, the world is going to be hybrid, right? There's going to be some classic ways of connecting it, this new cool way of connecting with the Ethernet drive. Does Ethernet drives make erasure coding better in the sense that compared to doing it the classic way?
I think it doesn't change anything. I think it's very useful.
From the protocol's perspective, I don't think it matters. But like Ignacio said, I think it is interesting that the recovery doesn't have to happen with the CPUs that's directly wired to it. That's what's good. Is that I can realize this network connected drive over here is now the data on is being repaired by the CPU that's in a different DC lane even, and I don't have to worry about physical connectivity being the requirement for where the recovery happens. And in that sense, I'm actually I think it'd be really cool, for example, in Swift world, to say, what happens if we had a rack of servers that aren't involved in the data path, but simply just doing the offloading, the replication, the auditing, stuff like that, which you can actually do if you can decouple those things. And that way you really lower the requirements on what is in the data path for the client, but you can offline and optimize the stuff that's happening on the capabilities, which is really kind of cool. It's exactly what actually we're probably going to do with erasure codes.
So yes.
Yes, the answer will be
Alright,
yes.
that's what I was looking for.
It's
There's studied aggregating non-kinetic drives and then having a traditional controller layout so that instead of putting half a gig of memory and more processor on a kinetic drive, moving that up one layer and having a device that has the kinetic interface but has 30 conventional disk drives underneath it for 15 gigs and a faster processor at a higher level.
But if the device has the kinetic interface, what do I care as the user of the storage? Right?
I'm saying use non-kinetic drives because they're cheap. They have less complexity.
Maybe, but at the same time,
The model would. I mean,
essentially, what you're
we
saying
support
is
that if you
grabbing grabbing some 20 or 30 of this and putting only one of these ports at the beginning, talking to all the drives, give it or take.
No, I'm saying use a less complex, less DRAM on each drive and move it all up to the traditional design. You could still, the kinetic interface would still support that. Sure. Because it would look like one large kinetic.
So, better yet, in 3 years, when HGST and Seagate Toshiba come out with their petabyte hard drives, and it has a kinetic interface on it, I mean, that's basically the same thing, right? It's just a smaller form factor. From the application perspective, it doesn't matter, because you can build your own device that says this implements kinetic, and we just happen to do it some other way. I think the hard part you would run into if you're trying to do that is the fact that in order to have those SAS or SATA connectors and expansion ports and all, that whole bus level, instead of the drive connecting directly to the top or right switch, then you're going to have some additional costs there that are probably going to wipe out any advantages.
Yes, but you don't have to have, if it's all one device, you don't have to have SATA or SAS or whatever.
So I think the difference, though, is if you look at those sort of things, that's basically what you treat it as. This is my failure domain. It has 2 plugs in it and done.
And the kinetic model will support that also.
That's actually, I think,
That is what that.
Yeah.
It makes it look like a single large kinetic one.
Yeah, it looks like one big guy. I mean, you could. I guess the bottom line is, as system builders, they don't care. They're just going to see it as a really fat drive. Yeah. That's basically what's going to be.
My concern would be about the isolation of failure domains.
Yeah.
And the impact of losing one of those failure domains. Yes. I don't want a failure domain that's a whole rack of storage normally, or at least I don't want to do anything automatic when that fails.
Actually, we want to see each drive also for load balancing reasons because we can much more efficiently utilize the drive. Yeah. We want to see each of them.
Well, I was thinking more that if you aggregated many drives, that same resource, the controller resource, would be usable by any device. So if you're just talking one drive, you look up for you cut down on that 20% random read overhead.
Yeah, but as you get bigger, I'm not.
Anyway, you answered my question. It's theoretically.
It is a possibility.
Sure. Okay. Actually, I would go the other way with like Sally talking with Flash. You'd have the individual Flash cells rather than saying, hey, this is a multi-gigabyte or terabyte Flash device.
So now Kinetic has a set of interfaces, and the higher level application like Swift or Kinetic, they use these interfaces for their own use. Now there will be scenarios where some future releases of Kinetic or Swift will need some additional, will put some additional requirements on the Kinetic side. That you want some new interface APC or some change to the existing interface. So, what do you see? The future releases will put requirements to the Kinetic to change the Kinetic interfaces, or would you ever see having your own plugin inside the Kinetic? So which direction do you see?
What I can say is that And I definitely speak to what Scalar is going to have to do, but from SwiftStack's perspective, working with Swift and working directly with Seagate since before it was announced and all that kind of stuff has been actually really cool. And in that sense, we have actually impacted the kinetic design and API, looking and saying, here's the use case we need to do, here's the problems we have to solve. What you're talking about doesn't, how about doing it this way? And so from that perspective, yeah, working with Alan and team, Jim, and all those guys have been really good so far. I can't really comment on what that's going to look like 3 years from now when it's much bigger and it's a lot bigger ecosystem. But I would certainly expect that when you have something that, as I surely hope it will be, widely implemented and widely available, that there are ways to say, let's figure out how we expand the protocol and figure out the different uses, and that's going to come when other vendors are implementing it and when other people are consuming it. So it's kind of one of those systemic effects. I don't know. Our experience has been very good.
So we get some feedback early on to Jim and Ali and got the features in the drive, so I'm very happy about that. Good work. So the thing is that we want to make sure that the drive gets out now. We don't add any features for now. Just get it out. It's stable, it's out, and we can use it. After that, there's a lot of features we can think of. For example, best compliance and WARM, being able to make sure that some data hasn't changed and modified. Kinetic as a checksum, they are able to do scrubbing as well. So is there a way to link the two systems so that you can do software-defined WARM offerings, something like that. There's the ability to do multiple transactions on different objects inside the Kinetic. There's a lot of flags we can think of to be able to get this I/O faster than the other. So there's a lot of small things that we'll be able to do. The protocol is flexible enough and loosely coupled enough that you can update it without breaking the old state.
Yeah, I would just add one thing, which hopefully this is a first indication of how serious we are about making this a community thing. We truly do want to factor in input from anybody and everybody, right? They're obviously at the very beginning, but the reason it's all open source is not accidental, right? We truly do want to facilitate a movement towards a new industry standard. We just simply didn't want to go down the 5-year ridiculously cumbersome traditional standards path.
You're more than welcome to go to Kinetic API protocol on GitHub, fork it, and do any changes you want, and after submit a change request, explain your changes, and then it will go through the review process, which right now includes several people from within Seagate. But eventually, as the ecosystem gets bigger, the review board will get larger. But the protocol's there, you're more than welcome to grab it and change it.
So, follow-up question is, you don't see any requirement right now to go inside the drive and have your own software when you inside the drive?
So I don't want to do that.
I have a different view on that, actually.
You want to support code on the drive?
As long as I can update it, I think it would be awesome. So there's kind of two perspectives on that, and both are represented in the room, which is fun. So one of them is I want to. The overall story of everything is how do I increase density, therefore lowering costs. And you can do that either by saying I'm going to do something like the Kinetic and kind of move that away and put it over on the network, and that's what the whole thing is about tonight. The other way is to say that essentially the Kinetic story is how do I have more drives behind one particular CPU of that storage application. And you can now have thousands of drives behind that. Ignacio said, let's have my laptop running in exabyte RAM. The other story is how do I go smaller smaller CPUs with a particular spindle or something like that, more along the lines of what some of the other vendors are doing. Both of them are the same story with different paths, and they are both very interesting. I really like I can run my code on this drive because I can do that today, and that's actually really interesting, and I don't have to change protocols of what I'm talking about. That's really interesting, but the Kinetic stuff is also really interesting because I hear about the protocols, I hear about the drives, and I think this is like 3-4 years after Swift was released. It's the drive that Swift was made to run on. It's kind of cool, and so it's really a nice match. I like both stories, and from my perspective, sitting on top of the hard drive vendors, my job is to abstract away what you guys are doing. And my whole point is that applications don't have to think about the hard problems of storage. Let me do that, and I'm going to abstract away storage. And sometimes that's going to look like a chip on a drive that I run my code on, which has some advantages. Otherwise, it's going to look like something like Kinetic, which has different advantages. But I like them both. Both of you keep doing your good stuff, competing, but I'm going to win.
And Intel servers are still pretty cool. It depends, of course, right? Yeah, so, no lock-in. Everybody, we're all happy.
Yeah.
I mean, not speaking as Seagate right now, but I mean, a pretty cool possibility that something like the drives would allow you to do. It's not like ship any random code down to the drive, but if you could do like the first step of map reduce function or open search on the drive and issue that as a command, that would also be like something pretty cool for certain applications. So you're actually using that the CPU and the ability within the drive, you're only shipping data out of the drive. But that's like, those are functions that are specific with the fact that you're actually storing data. Open compute, like any kind of code running on the drive makes no sense. The drive's not a CPU for you to be running code. But obviously things that actually support and allow you to ship less data out of the drive and can actually give you a benefit in reduction on energy on your data center or reducing your total time that it takes to compute, blah, 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 blah. That's actually, that would be super fucking awesome. And I mean, the ability to do that as we evolve is there. It's just a matter of slowly incrementing and deciding what's the cool way to do this. Is something that the community is interested in? Yes. Do we have enough people interested? Yeah. Okay, how do we actually come up with a solution? Oh, we have different ways. Okay, let's give it a try. And since we have the simulator that's also open source, implementing and checking, validating those ideas is also like pretty straightforward. Just like clone the, fork the simulator, fork the protocol, and fork any of the libraries. Do the changes on the protocol, have the fork on your simulator use that, have the fork on your client do that, and then check your idea. Does it work? Yeah, it works. And it's pretty simple to see whether or not that's actually something viable.
Do you have a form of kinetic drives when you say simulator?
The simulator is a Java application that is completely 100% compliant with the Kinetic protocol. So it's essentially a drive on software.
Do we have drives available?
Right.
There are thousands of drives out in customer test environments already. And we're going to be, I think we've said publicly we're going to be shipping the second half of this year, production.
No. My question is, I was confused when simulator was used.
Okay.
Can I write an app, and then have that app access some drives that you kept aside for, community?
You can actually do that
simulator
because
is software.
Yeah, you can
have
Simulator
you can spin like thousands of simulator. You can actually like rent some Amazon space and spin out like hundreds of thousands of simulator. Really up to you.
It's not
or having
touching
your
any
laptop.
drives. Software.
Yeah, and actually, if you can add to that, I remember when we were first told about the simulator, it's one of those things that those are kept tightly coupled, as in like if the drive isn't doing what the simulator's doing, the drive has a bug sort of thing. I mean, it's like that the simulator's going to actually do the same thing.
So can I take, is your simulator code also open source?
Yeah.
Okay.
It's under Kinetic Java. If I'm not mistaken, Chemi?
Yeah, Kinetic-Java.
Yeah, Kinetic-Java.
So I can take your hard drive and make it an SSD, write my own simulator.
No, we already have the simulator for you. You could use the simulator we provided. It's open source. You can start thousands
I
of
think I got the
instances.
answer.
Yeah.
Your experience with the simulator is great for the protocol. It behaves the same in terms of commands and stuff. If you want to do performance tests, you need a WinDrive.
Yeah,
Yeah.
And the drive is not in Java. That's the question I asked.
So the simulator have any requirement, any memory requirement?
It's a Java, so the memory requirements. So I mean, bottom line, yeah, but I think the reality is, what are you going to be using that specific instance of the simulator for? Are you going to be storing large amounts of data, so just like pass -x 5 gig or xm 5 gigs, and that's going to serve 5 gigs for the freaking Java instance. You can also you can launch the simulator with like any number of simulators running within the same Java process instead of actually having one Java process for each simulator. That's going to make it slightly more lightweight, and you can run on your lab like thousands of them at the same time. Doesn't matter. But I mean, memory requirements, other than that, how much data you're actually storing on it, and if I don't pass any arguments, I do make Java run out of memory pretty quickly. So you need to pass the extra arguments to actually get the Java allocation memory to be larger. But other than that, I mean, it's just basic Java problems.
Normal.
Yeah, it's normal Java problems.
Basic Java.
You had a question at the
So you guys talk a lot about how you love abstraction, right? How it has new API, good like files, and it's just about putting objects on this is a good thing, right? Look at that on actually. How much you want to have like all the full details of all the abstraction into what is going on. Like I give many examples of where you can actually dig around like in the Linux source code actually define like file system bugs or how some your behavior, performance problems, other issues. And that's going to be harder to do now, right?
So actually we're gonna, but just something I wanted to say before that. So actually we ask for a lot of instrumentation, knowing when code compaction is happening, knowing when the drives find an error, so that's done. But there's a lot of instrumentation that we're going to ask Seagate to implement in the drive, so that we get the data.
There are absolutely times you're really going to want super low-level access and direct access to hardware and know exactly what's going on. My perspective and what I'm coming from, I guess the anecdote I had, I was talking with our sales guys in New York one time, sat down for lunch with a hedge fund guy, and he was like, so I'm thinking about using Swift, and can you do like less than millisecond read times? And I just kind of laughed. No. The point is, yeah, but that's not really my use case. So my use case is the large unstructured data storage that is not the super, it doesn't have the requirements of those super low level things. So I'm worried about density. I'm worried about overall cost. I'm worried about being able to have that distribution spread out across thousands of drives. I'm not saying that. I know particularly that when this particular flash cell died that corrupted this part of XFS, getting away from some of that is actually good to me.
Sure. We saw a very similar problem to HDFS-ish, right? And we're also thinking of topics like single node performance, but we have still, I think, around in thousands of code time, weird behavior to diagnose things, right? You want to do something like make a flame graph what the kernel stacks are doing is super useful. And yeah, that's not.
So, except that today, if you're doing that, that's the code. It's where your application is running. So it's on that kernel, it's on that CPU. That's that. You're not actually digging around in the code that's running on the other side of that I/O bus. So
now
that's kind of the.
There, right?
Wait, that's what?
Now there's more code there, right? They're doing an action, they're doing this key value interface. That sounds more complicated to me than what's happening before. So.
Yes. Well. I'm not going to comment on that part of it.
Well, something newer also.
But the point is, from the layer of abstraction, it's the same. As in, like, I know that I'm not debugging the firmware that's already on the drive. I know for a fact there's bugs there. But just because there's code there, so therefore there's bugs. But I'm not debugging that firmware. And even if I had access to it, I'm not going to be able to reflash that probably. So the same thing if it's on the other side of a network instead of the other side of an I/O bus. The difference is really latency, not my ability to access that code, right?
I don't have a problem. I mean, there is more complexity now when it's Kinetic drives than versus a drive, right? And this code is also newer, right? Than I presume the firmware that is already on Seagate drives.
When there's millions of them.
Yeah, I mean, if you actually take the millions of lines of code that are already on any single drive out there and you compare it with the lines of code that Kinetic might have, it's a minimum percentage, almost negligible percentage. But Jim, do you want to comment on that one?
Yeah, there's approximately 2 million lines of code in the drive today, and getting a lot more when there's a smartphone drive. And we believe that Kinetic is going to make the number of lines of code that drive significantly smaller. It eliminates SATA.
Over time.
Compatible with the fastest card.
Over time, I mean, currently, your point is correct. Clearly, this is new code, right? But all I can say about that is that Seagate ships so many of these things today, and there's a quality thing. So we're not going to. Certainly, it's new, but it's going to go through all the Seagate standards to make sure that there's no change in what you're expecting.
I used to work for this guy. We really haven't seen people freak out about quality and code. Talk to this guy users. They don't care about it, and they don't do these things today.
shipping in something that can't be changed in a broken, with a rare exception, files can't be changed. It's a really, really big quality. So, I mean, IT, I think like block structure and action, I get very worried that we have issues with our similar key value rate. Exactly. So it's not just a sort of hard to do. It's difficult to
SSDs pretty much also have a similar thing, right? SSDs pretty much have a similar thing, right? Pop action.
Guys, we're gonna move on to the system builders panel now.
Hey guys, thank you very much.
Yeah!